Okay, good. Then I start recording, and afterwards you need to take that video of this one here. Okay, good. So last class we talked about convolution and the fact that it's a very easy to implement, very powerful, very flexible algorithm for doing all kinds of processing on an image. You can do things like change the brightness of your image. How would you do that? So if I want to make the image darker or brighter, then what can I do with the convolution mask?
All in 0 and result is maybe 0.5.
Yeah. If everything is 0 except 0.5 here, then that means the brightness value of the pixel is going to be half. And if I want it brighter, then I could change this to a 1.2, for example. We can use it to blur images, we can use it to sharpen images, we can detect different patterns in the image, things like letters, like the shape for the letter A, I can scan through. If you know the font, then you can go through and find all the letter A's in your document, things like that. And we can use it to detect edges by estimating the gradient of the image function. Right? So the most famous one of those would be -1, -2, -1. One would be the Sobel edge detection operator. Now, the Sobel detector, Sobel edge detector, has a couple of drawbacks depending on your application. It may work really well, or it may have some problems. So, one of the problems with the Sobel edge detector is that if you have an image and you have an edge that you want to detect, where this part here is black and here we have white, then since the edge will not be perfectly aligned with the pixels in your image, right? We're only sampling certain points in our image. That's where I have the pixels, that's where I have the sensor, something like this, for example. Then the actual changes in brightness may look like that. And our Sobel edge detector is a first order operator which simply looks on the change in your image function, in the image. So here we have an edge, but each one of these may trigger maybe above a certain threshold. So in that case, your output image would be, instead of what you want would be this, right? black, here's your edge, everything else is white. But you may get something like that. Where you get 3 edge pixels then, side by side, adjacent to each other. And that's a common problem with the Sobel edge detectors and other edge detectors that are all based on the first derivative. Now we'll try and look for ways in which we can overcome this particular problem. And that would be called the Laplacian operator then. So last time we looked at the scene from Casablanca. So here's the scene from Casablanca, grain scale image, Humphrey Bogart. Oh. What are you guys doing there with the computer?
I touched the batteries. The plug.
Okay, don't mess with the plug then.
The
So here I have a second order derivative. And how do we use that in order to detect edges? Now, first of all, why is that a second order operator here? Why does that particular matrix that we have here, why does that calculate a second order derivative? So the problem that we had was that really our edge is not a ideal edge, but it's one that we actually get from our image. So it looks like this. And then any one of these here will have a high gradient. We get lots of them that are together. So how can I solve the problem of these various edges that occur? If we think of this as a function, then right now we would calculate if I don't think about computer vision, if I just look at this as a function with one variable, and this would be f of x, then f dash of x, the first derivative, would be the tangent here, the slope of the function at that point. And we can calculate that using a convolution mask. Like this, for example, on a single row. And in that case, I calculate the first derivative by taking my right neighbor and subtracting the left neighbor, which gives me how much the function actually changes. Which is why that is an approximation of the first derivative. Now, for the second derivative, what is that? Well, the first derivative is how much the function changes, so the second derivative should be how much the first derivative changes. Right? It's a derivative of the change in the function. So now I want to be able to come up with a convolution mask that allows me to estimate how much that function is going to change. How much the derivative of that function is going to change. So the way I want to think about that is that I need two derivatives, right? So I can take those two. this is this one, and 2 of x would be the change in the derivatives. So one derivative I can calculate by plus 1 minus 1, right? This one minus this one will give me the f dash of x between those 2 pixels there. And the same one would be here, plus 1 and minus 1. That would be the derivative between those 2 pixels. So now I have the derivative, the first derivative for both of those. Now I want to see how much that changes. So I want to take this minus 1 plus 1 minus, and then this minus 1 plus 1, where the minus 1 would be the center pixel. This would be this one, so the right neighbor. And this would be the left neighbor, and this would be the center pixel. Because here, this would be plus 1 on the center, left. This would be center and left. Not left, right. This would be the right pixel here. So now, if I break that up, then I get minus 1 for the center pixel plus 1, right? Minus is plus 1 for the left one, minus 1 for the center one. Which, when I group it together, gives me plus 1 for the right pixel, minus 2 center pixels, plus 1 on the left pixel. And when you look at the convolution mask that we use in that image, the same thing would be true if I were to estimate the top and bottom rows, right? So if I were to calculate the second derivative in the columns as opposed to the rows, then I end up with the same. So if I add them all together, I basically get plus 1, plus 1, plus 1, plus 1 minus 4. Or, since I don't care about the sign, whether it goes from positive to negative or negative to positive, I could also switch the sign. So I can have minus 1 outside and plus 4 inside. Both of them are the same. And so this is how we end up with this convolution mask here. This is why this convolution mask estimates the second derivative of the image function at that pixel. It's just a lot easier to understand when you see the minus 4 and the 1, 1, 1s around, why that actually occurs, as opposed to introducing it as the first or second order derivative. But this convolution mask is an approximation, an estimate of the second order derivative in the image. Now, how would I use the second order derivative in order to detect an edge. Well, there's two ideas. One would be to just look for a strong response, because here, the second order derivative in this area here would be constant. Right? Because the change in the slope is the same, pretty much. And in this area, it will be constant as well. Just at this point here, there will be a big change, a big switch. In fact, from a positive number to a negative number. For the second derivative, you can think of it as telling you the direction to turn when you drive a car. If you need to steer left, then your second derivative would be positive. If you need to steer to the right, then your second derivative is negative. So that's why we have a strong response only at this particular point here, where we switch from a left turn to a right turn. As long as you keep turning right, the second order derivative is not going to have a strong response. That's one way of using this second order derivative. Another slightly different approach to detecting edges using the second order derivative is called the zero crossing. In that case, you actually check in your image, you calculate the second, you estimate the second order derivative, and then you pick all the points where it switches from positive to negative. Because at that point, that should be the center of your edge. And there should only be a single response that you get at that point. Both of those operators are pretty, in practice, they perform equally well or equally poorly. There's not that much difference between them. So here in the grayscale image, and then convolve it with our Laplacian operator, and then here I threshold the image with all the second order responses, Laplacian operator, where the Laplacian operator is within at least 10% of the maximum. So let's try that with 0.5. And then plot the figure. Here will be our just threshold the image like that. See what the maximum that image. So I want to resize the image. Otherwise, the pixels will disappear. Yeah, so that's a little bit better. So this is the response of our second order operator, and also I can so let threshold at any pixel less than 0. We shall set to 0. Looks nice, maybe too few. Take the threshold. So now I just highlighted the edges that we got from the second order derivative, and just so that you can compare them, let's implement a Sobel edge detector as well. One, 2, that should be 313. Here we'll make that bridge 4, and the convolution mask that I want to apply is the Sobel edge detector. So here I'll just take the So here, this would be our Sobel edge detector in the horizontal direction. So you can see that the lines are thicker here, so we get multiple edge pixels along the row. Here in this part, let's just curve. Count. And here's our second order operator. Now, make the comparison clearer. I can also threshold this. So So let's try and find a similar value. Max of image 4. Maximum, so 0.1, set it to 1. Set this and otherwise 0. So now we use the same kind of coloring. Image 3, 1. So that would be the difference. This is a sole edge detector in X. Here is your Laplacian, your second order derivative. You can see that it actually does a nice job with thin lines. Right? Like here, the outline of the police officer, the metals are all a single pixel only, whereas here we have multiple pixels running across. Here the trench coat, Humphrey Bogart's trench coat, has many different pixels here, whereas there's just a single line. So, because of that, and since it's implemented as a convolution mask, there's basically no difference in the performance of the algorithm. The runtime is going to be identical because we're just running a 3x3 convolution mask over the image. What these numbers here actually are, right, doesn't really matter to the CPU. The CPU will just calculate the multiplication and then add them all up together. So that's looking pretty nice. That's exactly what we wanted. We wanted to avoid these spurious edges that we have multiple edges side by side. That doesn't make any sense. But it happens in natural scenes very common. Because the brightness response is just like not fixed on a single pixel, black and then white. There's some overflow between the CMOS sensor elements. So now we can look at the zoom view of that. Just zoom in. Uh, 640 by 480. So make that 50, 320 to 410. Here we have the zoomed in view. That's somebody's shoe. Here's our mask, and this would be the output. Select ND, divided by 2, 3. So far, that looks great. But the largest, like I said before, this second order operator, the idea is to solve or fix the problem of having too many adjacent edge pixels that are, or edge pixels that are adjacent together to each other, because then that's one edge, right? There's not 10 edges that just happen to be one beside the other. That, as we can see in the image here, our edge detector, that problem it can solve very nicely. The difference between, we get a single line output using a second order operator. So that's nice, but the problem is in areas where you don't have an edge. So if your image function is like that, continuously, no change in color, then of course your second order operator is going to be, the output of the second derivative of this would be that would have to be 0, right? Because there's no change. So that means f dash, first derivative is 0, second derivative is 0. So none of the operators are going to give you any response for an edge, which is correct. That's what should happen. Now, if, however, we have some noise, then our image function may actually look like this. Very unlikely that you get exactly the same pixel level all the way across. There's always some noise in your camera hardware. So this is not going to look so flat. It'll look like this. Now, the first derivative is going to look if this is to scale, so here 0, 2, 5, 5. Then here you may end up with being like 3 pixels too high or 2 pixels too low. That means your first derivative is going to be non-zero, but it's going to have a very small value. Because you just go up by a little bit, go down by a little bit. Right? In order to detect an edge, you would have to do something like this. That's where you would detect an edge. But these small ups and downs are not going to affect are not going to trigger your Sobel edge detector. But what happens now with our second order derivative? Now the second order derivative looks for changes in the slope. Right? So that means that here I'm going up, here I'm going down. So as far as the second order derivative is concerned, that's actually a pretty big jump. Right? Here I'm going down, then I go up again. Then I go down, then I go up again. Go down. And here I go really up. This one actually, the second order derivative is going to pick this one as a single line too. But it also is going to give you all of these edge pixels. And that, of course, is brutal if you have some noise in the image. Then your second order derivative is going to pick up each and every, because it doesn't care if it's +1 or -1, but there's going to be a big swap in the second order derivative at that point, a big change. So here I have an image, and we zoom in on Humphrey Bogart, and that is the zoomed in view. That's what I wanted to show here. So now I take the image and I add a random noise with a magnitude of 20. So That's about 10%. That's not a huge amount of noise in the image that I add to it. And then we can see what happens. So the Laplacian with noise gives you this, which is basically useless. The little bit of noise that we added to the image here, you cannot really see it. Like visually, if you look at that image, you may see that it's a little bit grainy, but it wouldn't be, where's the girl? I cannot see her anymore or something. Right? This wouldn't impact your vision at all in trying to recognize it. You can probably see that the image quality is not as good as before. There's some grainy areas here, but not nearly enough to throw off your vision. But as far as your Laplacian operator is concerned, it now detects edges everywhere. Right? Now you just have a mass of edges everywhere. So that's the downside of your Laplacian operator. If you do have noise in your image, then it is extremely sensitive to noise. And so at this point, that particular approach would not work for this image. So instead, what we need to implement, so in order to use the Laplacian operator in a practical application, no, I have one.
那他们会保角色，角色。
Let me share the link. So here we have a different image of Wikipedia of bird. And then before, instead of implementing the Sobel edge detector by hand, I use the built-in Sobel edge detector from the OpenCV library. So this gives me the gradient in the x and y direction, depending on the kernel and the size of the Sobel edge detector. And we can show the output. And here, that's pretty nice, right? We get a strong response for the bird with some additional false positives here. There's some return on the leaves and stuff. But we certainly would be able to extract the basic outline of the shape. So if I add them together, then I can threshold pixels, x and y gradient added together, and then here's a zoomed in view of this part of the bird. So here we can see multiple pixels per edge, but we would like it to be just a single pixel. So the Sobel edge detector uses the first order derivative to detect an edge. Two adjacent edges, two adjacent pixels may have a high first derivative. And the second order derivative allows us to distinguish between a minimum, a maximum, and a saddle point of a function. That's basically. If you remember in high school, when your teacher asked you to find the maximum of some function f of x is 3x cubed minus cosine x or something like that, then you would have to first calculate the first derivative. Then the first derivative on the maximum point should be 0, so you would look for the 0 points of the first derivative. Once you find those, then in order to prove that it's a minimum or a maximum, you still have to calculate the second derivative and then check that your second derivative is, if your second derivative is positive, it's a minimum. If your second derivative is negative, it's a maximum. If your second derivative is 0, then it's not actually a minimum or a maximum, but it will be a saddle point like this. This point is neither a minimum nor a maximum of your function, but the first derivative would be 0 here, right? So that's what we're trying to use the same trick with the second derivative in order to figure out what kind of pixel that is, where that belongs. Is it a minimum or maximum? Or in our case, we're looking for saddle points, right? Because this is where it would switch from positive to negative. And we would locate the edge. So we can calculate the first derivative of the image function I dash x of y greater than some threshold, or we can look at the second derivative and then find areas where it switches from being positive to going negative. That would be the zero crossing operator. Now we can derive the equation for the convolution mask for the operator. Here I did it for a 5 by 5 as opposed to a 3 by 3 version. This is the pixel that we're interested in, 0, 0. These will be our neighbors. So this is P0 minus 1, P0, 1, P0, 2, P0 minus 2, P minus 2. So our it's a 5 by 5 kernel. And like we did on the board, given the image function in the x and y direction, I take the left neighbor and subtract my right neighbor, or the neighbor above minus the neighbor below minus the neighbor above. -1 here. So then I need to calculate the change in these derivatives. So here are the derivatives. And I subtract them, and I get this pattern for the row, and then the same for the column, which is why we end up with this convolution mask. So that would be the 3 by 3 neighborhood. In this case, I only check for vertical and horizontal edges, but of course I can also check in the diagonals, like top right, bottom left, and top left. Right? So I can check in all 8 directions as opposed to just the 4 directions. If I do that, I end up with this convolution mask, where I have 1s all around and -8 in the center. Right? It's basically 2 of the aligned Laplacian masks added together after I rotate one of them by 45 degrees. So this is the mask that is usually used for Laplacian operator. And then you can have different kernel sizes in order to calculate that. So 9 or 7. And we can apply it. Yes, the grayscale conversion. In that case, I just use the convert color function. And then you can have an argument here. You could also have color RGB to HSV, for example, if you wanted to do a conversion to HSV color space or something like that. That's possible using OpenCV. This is the bird. And then I can apply the Laplacian operator as well as the 2 Sobel operators. So here's our output. This is a Laplacian operator. And so this is what it looks like. And here we have some extra edge pixels. Here we have a single line. Switches nicely. And I can zoom in on parts of the image. And we can see the difference. So this would be the actual third party glass. Laplacian and the Sobel. And now we add some noise to it. So here's the original image. Here's the image corrupted by noise. Now the noise is uniform distributed. No, this time it's a white noise, so it has mean of 0 and standard deviation of 5. So it's a Gaussian noise that is added to it. So I get rid of this extra factor here. Here's the zoomed in version. And then we can apply our edge detector. And here's the output of our Laplacian. Basically has edges everywhere. Like the whole area is white. Only because I added this noise. Very tiny amount of noise. So I guess because the lecture slides are called Laplacian of Gaussian, the solution to that particular problem is that we have algorithms for getting rid of noise. So if noise is such a big problem that it will make my Laplacian operator basically useless, then before I apply the second, and this is not just the Laplacian operator, this would be any operator based on the second derivative. Before I use it, I make sure that I remove the noise as much as I can. And that operation, if we remove the noise, then that operation is called a blur, right? We're blurring the image. And we already said that we can do this with a convolution mask, because if I set it 1, 1, 1, 1 everywhere, and then divide by the 9 in this case, then I would end up with the average of all the pixels in the neighborhood, which is exactly how you can remove noise. So you're basically taking all the small changes and average them out over a region. You can use 3 by 3, 5 by 5, 7 by 7, 9 by 9 masks. In order to do that, it depends on how much noise there is in your image. So instead of doing the instead of just calculating the average using a mask of 11111, we can be a little bit smarter, because if it is two-dimensional Gaussian noise, then it should sort of look like this, the distribution. Along the row, and then of course this would be three-dimensional, so it would be like this head shape here. Like that. And then that means I can put more weight on the pixels that are close by and less weight to the pixels on the edges. So instead of just having equal weight, 11111, I can play around with the weight, put more weight onto the center pixel and less weight onto other pixels. So, but of course, I only have a convolution mask. I still want to implement this as a convolution mask. So I cannot take all the pixels, all the points here. I can just take certain points where the pixels are. And the get Gaussian kernel function in OpenCV, it returns the Gaussian kernel for a particular size. So here, size 9, for example, or size 7. Now, if you use a 3x3 kernel, then basically the standard blur with 9 is probably as good as it gets, because there won't be much difference in the values. This would be more for larger kernel masks, like 7 or 9 pixels. And I guess we can print out what K looks like from 9 by 9. Now this is symmetric, so you just get 9 values. Oh, 7 values. Oh, because I set it to 7. So this curve here that we're estimating the calculation, and that's the. And just out of interest, I never looked at what 3x3 actually looked like. Okay, quarter, 50%, and another quarter on the third pixel. And 9 will give you a better approximation of this curve. So now we use that kernel and apply a Gaussian blur with that size in order to remove the noise before we do anything. And then I can apply the Gaussian, the Laplacian operator, as well as the Sobel edge detectors. So here's the output then. Now it looks nice, right? I don't have any huge amount of noise here anymore, so not many spurious edges. But because I had to do the blurring, that means that in certain parts, I will have, most likely I will have washed out some of the differences. So that means that now my outline is only a single pixel wide, but it has holes in it now. Right? There's a part of the outline here that I'm missing. Here's the output of the Sobel X Y detector. So we have strong response here. This part here, for example, we have too many pixels, but we don't have any holes. So here's the output of our Laplacian or Gaussian on the image with the noise added. And here, in comparison, our Sobel edge detector. Now, as you can see, and I mentioned this already several times before, anytime you have a classifier, doesn't matter whether you use machine learning or computer vision, then you have to think about the both types of error, the false positives as well as the false negatives. Because in most applications, the penalty for one is very different from the penalty of another one. If for our ball detection, for example, one of the hardest things if you implement a computer vision system for robot soccer, like in this video here, I don't know if I've shown this before, but this is was a pretty fun project that we did with the students. So here we have little tiny toy cars that are RC cars. So they were connected to the parallel port of a PC. Then we have a vision system, basically like a webcam, pointing on the playing field. And the playing field was actually a television that was rotated 90 degrees. And then, so the robots are real, we track them with our vision system, and then we implemented Pac-Man. So because it would be very hard to build a tiny robot that can pick the little pellets up, the power pellets, right? But on the television, the vision system was tracking everything, so if the Pac-Man drove over a dot, then it would eat it and would make the sound, and then the strawberry will show up. And there's a single dose. So now the Pac-Man was out of the video and game over. So this was a lot of fun. For that particular video, the vision system Here's another version of the same thing. So before we did Pac-Man, we did this obstacle run. So there is the television, the robot. Here you can see the camera, and we have purple dots moving around the playing field. And the challenge was for the robot to drive from the left side to the right side without being hit by any of the purple dots as they're moving around. And then the more you can do that within 5 minutes, the better your score will be. So then he got hit there. Here's the view of our vision system. That one was actually quite popular. There were quite a few teams worldwide that were using it. And you can see how it's tracking the playing field and the robots. Now, what's the hardest thing for the vision system in detecting the purple colored dots? Actually, one of the hardest situations was when there were no purple dots there. Similarly, when you're trying to play soccer and you're looking for the ball and there is no ball in the image, then that's actually really difficult to say, because we implement the algorithm to basically try very hard to find anything that could be the ball. Because most of the time there is a ball in the image, and we want to make sure that we get it. If there really is no ball, then our algorithm would still generate these phantom balls, or phantom purple dots. And in that case, that caused a lot of problems in our algorithm. So we had to change our computer vision algorithm, because if the robot, if there's a ball in front of the robot, right, and we get a false negative, which means we missed the ball, the robot didn't see the ball in the next frame is still there, right, and the robot will have moved a little bit. So now it has a pretty good chance that it will recognize it at the next frame, right? So false negatives were not such a big problem. But a false positive, if the ball is over there and the robot looks this way and sees a ball, then it just keeps walking in that direction because it keeps seeing a ball in front of it. So it's chasing these phantom balls, which means that it would end up on the edge of the playing field just looking outside without, which was not very useful for a soccer player. So in this case, the false positives were much bigger problem than the false negatives. Other applications have other trade-offs. And the most important thing to realize is that any classifier you develop will have this trade-off. The error rates are usually not symmetric. And the penalties for the errors are also not symmetric. And certain algorithms have certain tendencies. So, for example, with the Laplacian of Gaussian operator, here, because it's too extreme. If we look at this picture here, and we compare the performance of the first derivative operators, the Sohel, and the second derivative operators, the Laplacian of Gaussian, then you can see that the result is very typical. Like here, we have a very nice thin line, so we don't have many false positives. In this picture here, there's hardly any. There's a couple here. Right? Those two that may not actually be edges. But they're very small. Other than that, no false positives. But we do have false negatives. So here pixels are missing in our outline. If you're trying to detect the shape as a bird and the pixels are missing, then depending on what algorithm you use, this may have made no difference at all, or this may make it a huge problem. For the Sobel edge detector, much more likely to have too many edge pixels. We have spurious edge pixels here on the strong edges. We also have spurious edge pixels in the leaves, in the forest. So if your algorithm does bad things, if you have false negatives, then false negatives, so you say it's not a pixel, then you don't want to use the Laplacian Gaussian, right? Because you're more likely to have this kind of error in this algorithm, much less likely to have it in the Sobel-based approach. If your algorithm works poorly with false positives, then you want to use the Laplacian Gaussian. Okay? Because it's going to give you much fewer false positives. So it's important to be able to think, it's important to think about these trade-offs, and then also think about the algorithm, exactly what kind of error profile they have in general. So the best choice of edge detector, there's no optimal edge detector. It depends on your application. Your Sobel operators have the advantage, or the pros are that they're robust to noise. It's easy to complete the outlines because you have multiple pixels along an edge. If that's a problem, then that would be a negative. And you may have false positives, extra edge pixels. The Laplacian operator-based ones, the advantage is that you usually only get a single pixel edge. So your edge is only a single pixel wide, which is nice. But they're sensitive to noise. So that means if you do apply them, you have to blur the image first. And then that means that you may end up with holes in your outline. So every classifier algorithm, there will be two types of errors, false positives and false negatives. In practical applications, usually the penalty for one is very different than the penalty for another one. So you can have a machine vision system that detects error in a painting job or fits circle to ribbon holes. In this case, false positives would be a bigger problem because the part would need to be checked, which may be expensive. And in New Zealand, we were working on a system for the Le Frito company. They were making potato chips. So the potato chips will come down the assembly line, and then if the chip was too moist and you vacuum seal it and then put it on the shelf and somebody buys it, then it's very gross when you open it. It's very disgusting when you open it because all the mold will be in there. So if you get one of those bags, you will never ever buy that potato chip again, that brand, right? It would be it would have a very bad smell and customers would be very angry. So in this case, a false positive saying, oh, this potato chip is too moist, you need to throw it away, Throwing away a single potato chip does nothing to the company really, because they produce, like, it's just like an endless stream of potato chips 24 hours a day, right? So they produce like thousands, hundreds of thousands of them per day. So if you throw away some extra potato chips, the company doesn't care at all. But if you put one of those potato chips into the bag and sell the bag, then the company has a huge problem. Right? So they, in that case, we had to tune our classifier to make sure that we do not have any false negatives at all, or as close as no false negatives at all as we could possibly do. Which meant that we added extra sensors in order to measure the moisture content twice, and the weight of the thing, and then it was going down, and then there was a little flipper that would throw away put the potato chips away if they were not dry enough. Now, this becomes even more interesting if you're dealing with domains where the penalty is very different, but you also have problems. A lot of the computer vision algorithms nowadays actually have a first step that includes machine learning or are entirely based on deep learning architecture, convolutional networks, things like that. So in that case, then, not only are your errors skewed, but also your training data is very skewed. Because if you want to build a vision system to detect if somebody is carrying a gun, right, or like supposedly some airports now have vision systems in the airport, and they are looking for micro expressions. Now, micro expressions is this theory that you can look at people, and just by the small habits that they have, you can detect if they're nervous or not, or if they are planning to commit a crime or something. So maybe if somebody does this, then that would be a micro expression, something like that. So, but if you think about implementing such a system, is even worse, because of course, not only are the outcomes very different, but also your training data. Let's say you implement a vision system and you look at people, right? Then luckily, the number of terrorists is very, very small. So if you capture 1,000 images of people, you will have most likely 1,000 innocent people, right? Because there's not that many terrorists, luckily. So then if you feed that to your network, what will the network actually learn? It'll learn like, oh, 99.99% of the time, if I say not a terrorist, then everything is good, I'm correct. In fact, the network could do that with a simple print statement. It will get 99.99% accuracy. Right? Because if out of 100,000 people, there's one terrorist, then if you say no, 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 you're correct most of the time. The vast majority of the time. So in that case, just getting the training data to make sure that it's not skewed, so that you can actually, the machine learning systems don't work well if the training data is so skewed. They expect that you train it on 50% terrorists, 50% normal people. If you don't do that, then you're asking for trouble, most cases. So that's another problem with more advanced vision algorithms or more advanced AI systems. The fact that your training data can be biased, extremely skewed sometimes. Okay, good. So the core of the lecture was about first and second order derivative operators, but also the more general lesson is about first order classifiers, tuning of classifiers, selecting parameters for classifiers, and then there are some methods that you can use to try and come up with ways to mitigate both your type errors by either presenting results as a confusion matrix or an F-score, or also how to think about the skewness or biases in your training data. Because anytime you have a neural network system, once your training data, if your training data is biased, it's virtually impossible to remove that from your machine learning system. And you wouldn't necessarily know that your training data is biased. It's easy to see that your training data is biased if you have 100,000 pictures of class A and one picture of class B, then anybody can see that, right? It's a lot harder when it's something like people's skin color or things like that in other transactions where you want to apply AI to. Okay, good. So that's it for now. So now for the next 30 minutes, you can pick your own image and then implement the Sobel and the Laplacian or Gaussian operator using the OpenCV library, and then compare the results for a particular application that you have in mind. So let's, what could we do? And you don't need to do a quantitative evaluation, you just need to do a qualitative one. So let's say you're trying to check you want to help improve the traffic situation in Taiwan. So look on the internet for some pictures of traffic in Taiwan. And then apply your lock and your Sobel operators and see if you can detect the outline of cars and how well the operator, which operator do you think would work better for this particular application? If they have 30 minutes.